the soil testing lab, we'll measure the phosphorus and potassium level and report that. We do not measure nitrogen. What is it about nitrogen that makes it so much harder than the other nutrients? When you send us a soil sample, we'll measure the phosphorus concentration. Once the number gets up to 55, above 55, you'll get no response. But when you look at the soils that we have that come into the soil testing lab, they range from below 5 to 500. So if I wanted to find these soils, where would I go to find a below 5? And where would I go to find an above 500? And why do you think this would be? If a soil has 55 parts per million, you can multiply that number by 2 and it changes the units because there are 2 million pounds of soil in a furrow slice per acre. You multiply it by 2 and you get pounds per acre. So there's 110 pounds is equivalent to 55 parts per million. So if you have corn silage and it removes 50 pounds per acre, what do you think the soil test will be the following year? Can you just subtract this 50 from the 110? And how and why would you want to increase soil organic matter? People have heard a lot about soil health, and a lot of that's tied to soil organic matter. So there are two questions here. How would you increase it, and why would you want to increase it? And I'll let you think about those, and hopefully Paige will be back on with us shortly.
Yeah, take your time, answer them. If you want to answer, one or two or three of them, please do. And you can just put kind of, if you want to answer predict plant available P and K, maybe put 3 in the chat and answer that question. Take your time, think about it. We're not gonna, no points deducted for guessing, wrong answers, anything like that. The more you can interact, the more you get out of the training. So type away, guys.
Yep, if you just sit and listen, you don't learn a lot. So it's a way to try and get some more interaction and get your brain working. And Stephanie, let me know if Paige jumps back in.
Will do.
It's hard for me to tell in presenter mode.
Yes, watching for her, but nothing yet, and I'll let you know.
And Stephanie, is there a way for me to see chat in presenter view?
Do you have 2 screens right now?
I duplicated them to try and get rid of problems.
Because I know I can see things when I'm presenting, but I'm using the app and not the web browser. So you can pull it up, but a lot of times I think with the web, maybe like do you see with presenter mode running down like icons with names in it?
Yeah, but they're like, I can only see 4 names.
Yeah, and you can maybe click through the bottom of them and see them. There might be a button up in the more section around there that will let you see the chat instead of the names.
Oh. Well, maybe you can just read them out to me if you see
Yes,
any.
it has nothing so far. Come on, guys. At least one question. These are we've talked about them pretty well over the past couple of days. So
Maybe I'll
remember, no,
start. Maybe I'll start going through them, and if somebody says something, you can read
I
it out.
will jump in.
Okay, first question. Why are yields and therefore nutrient requirements not the same in all fields? How many different factors can you think of? Anybody?
Talked a lot about different soil types yesterday,
Yep,
guys.
yeah.
Anything kind of along those lines? Is that jogging any memories? Water availability? we have from the chat. Land use.
Land use, so crop type.
Yep. Slope. Organic matter. You
Yep.
just needed a little poking.
There you go. Yeah. So yeah, obviously the crop type matters a lot. Something like a legume that grows its own nitrogen is not going to need as much nitrogen as something like corn. And even with something like corn, yields. You're not going to get the same yield across all different soil types. Hopefully you remember some of the values training from yesterday. So different soils have different capacities for different yields. Mostly that affects the nitrogen. Oh, here comes.
Yep, here comes Paige back. And we also had parent material and different plants need different nutrient distributions.
Yep.
As
Mostly it's nitrogen for the phosphorus and potassium stays fairly similar, but there are huge differences in nitrogen based on yield and soil type and crop type. Okay, I guess I can stop sharing and hopefully
fingers
Paige,
crossed, hit Paige
fingers
on.
crossed. Give it a try, Paige. So Paige, if you can hear me, I just finished the first question.
I
And
see she's
David,
unmuted, but nothing so far.
maybe I'll keep going until she can hear from us. So can everybody hear me again?
Yep.
And you can see my screen?
Yes, with the first question up.
Yep. So second question, nutrient management is harder on a dairy farm than a cash grain farm using only inorganic fertilizer. What is it about manure that makes management so much harder in terms of nutrient management?
Right out of the gate, we have someone, because it's harder to measure and time the amount of nutrients going into a dairy farm compared to a grain farm.
Yeah, measuring it, like when you buy a bag of fertilizer, it has to be analyzed, you know exactly. Oh, I hear Paige.
Yep, a little bit.
Great.
Very-
Although you're breaking up, Paige. Like your internet's not secure.
I'm not sure if I'm
In about every other word.
muted or not.
Sounds like your internet is slow. We're only getting some of what you're saying.
I think she just jumped off again. Who's gonna maybe restart her
Okay,
computer?
well, I'll keep going. So yeah,
We also had another one with manure has more variability in composition than chemical fertilizer.
yeah. I mean, when you apply manure, you need an analysis, but it is variable. For example, if you mix a dairy lagoon before you spread it, before you pump it out, the nutrient content may change a little bit as you're pumping out. So it's a little harder to know what exactly is in there. But one of the big things is the nitrogen to phosphorus ratio. You would think that because dairy cows eat mainly corn, the N/P ratio would be about the same. But during most of the air that we're breathing is nitrogen, so a lot of nitrogen is lost during the cycling, the nitrogen cycle. So manure ends up with too much phosphorus and not enough nitrogen compared to crop needs. And the basic of nutrient management is take a soil test and follow the recommendation. What happens if your soil test says you need to apply um, only nitrogen and no phosphorus? Or the other way around, say it's for soybeans, you only need phosphorus, you don't need any nitrogen. With manure, you're kind of stuck with the ratio you have. you can't change that ratio. And in terms of volume, you can't change the volume unless you change the animal numbers. So in the past, sometimes manure wasn't treated as a value. Yeah, but nowadays with nutrient management regulations, you have to look at the value of the manure and make sure you use it appropriately across the landscape. Okay, we predict plant available phosphorus and potassium by soil testing, but not reliably nitrogen. Why do you think that might be? Any thoughts at all, Stephanie?
There was one or two, one for the last one, but it kind of applies to this one of that it releases at different time intervals, and nitrogen is very mobile in the soil.
Yes, the plant available form of nitrogen nitrate can leach. It's very, very mobile. But a lot of this gets back to chemistry versus biology. When you add phosphorus or potassium to soil, it's stuck onto the soil through chemistry. And we're very good at predicting chemistry. So we can measure the phosphorus and potassium with chemistry in the lab, and we can project what percentage of that is going to be plant available. With nitrogen, about almost all of the nitrogen in the soil is in the organic matter. And the organic matter needs to be broken down through biological processes into the plant available form nitrate. And what happens is when the soil is nice and warm and moist, the microbes are happy and they break down the organic matter. When it's dry or when it's cold, it doesn't happen nearly as quickly. So we're not very good at predicting nitrogen release by the microbes because we can't predict the weather over a growing season. And once it does become plant available, the nitrate can leach, as somebody said. So, so if we know 55 parts per million in soil is adequate for crop growth, why do some soils test below 5 or above 500? Can anybody guess, if you wanted to go look for a below 5 or 500, where that might be? Nothing, Stephanie?
Nothing. Do you think you guys would see below 5 where there's lots of animals or where there's not lots of animals? Or crops even?
Well, if I was going to look for below 5, our native soils are very deficient in phosphorus.
Might
So
we look at trees? Anybody?
So if I went into a forest somewhere that had never been fertilized, we would find very low phosphorus, like below 5. Or sometimes in developments where the topsoil has been removed and not replaced, and people are trying to grow things on the subsoil, that would be a place we'd find very low phosphorus. For above 500, most people can guess, beside the dairy barn, where there's a very long history, especially before nutrient management plans came out, where there's a long history of manure, we find these high numbers. But we also find them in places like vegetable production, where you have a very high value crop. The other place is homeowners. Farmers do, on average, do a much better job than homeowners. For a farmer, their fertilizer inputs are a big part of their cost, so they want to drive those down. Whereas a homeowner, they just have a bag of fertilizer. They know fertilizer helps things grow, but they may not know how many pounds of nutrients are in that bag of fertilizer or the size of the area they're applying it to. If a soil has 55 parts per million phosphorus, you multiply it by 2 because there are 2 million pounds of soil in an acre furrow slice, you get this 110 pounds per acre. And you see this in the regulations and recommendations sometimes. So if a corn silage crop removes about 50 pounds of phosphorus per acre, can you just subtract that 50 from 110? Or what do you think the soil test would be the next year?
Does soil move fast or slow, guys?
It changes very slowly. I actually wish this wasn't in the recommendations, but it's in so many publications. It's hard to completely change the units, but it takes about 18 pounds of phosphorus to change it by about 1 ppm. So if you come back the next year, you're not going to change more than about 3 parts per million. Soil test phosphorus changes very, very slowly with time. And last question, how and why would you want to increase your soil organic matter. So let's start with the first. Why would you want to increase your soil organic matter? What does soil organic matter do that's beneficial for plants or crops?
We've had a couple, we see for increases yield, water retention,
What?
carbon with
Yep.
a question mark. So I don't know if they're asking if it increases or decreases carbon, but it was in there.
Water retention is a big one. So what we want to see is when it does rain, if you have more organic matter, your soil will hold more of the water. So it makes it much more drought resistant if you have more organic matter. Somebody said carbon. If you were thinking about carbon sequestration, building soil organic matter does that. There's also something about biology. Most of our soil testing is chemistry, but there's something about biology that plants love, and it's based around your soil organic matter and your soil structure. A lot of those things go up and down with temperature, so they're very hard to measure, and they go. A lot of the biology of the soil goes dormant in the winter, but we know soil organic matter is very beneficial for plants. They love it. And the second part is how. What crop practices or can you implement to try and increase your soil organic matter if you were a farmer?
There's some big cost share practices around it. Yep, cover crop.
Cover crops is the big one. Sometimes people say manure is a good way to increase organic matter, and it will increase your organic matter slowly over time. But the amount of organic matter that you put in with a cover crop far exceeds that of what you would put in with the manure. So cover crops is the big one for increasing it. And also tillage, or the lack of tillage. If you till a soil, you're going to decrease your soil organic matter, which is one of the reasons we promote conservation tillage or no-till. So organic matter is very good.
So I see Paige back. I don't know if she,
Yes, I'm back. Can you hear me okay?
Yep,
yes, can hear you great now.
Okay, amazing. I think my computer might explode if I try to share. So, Dr. McGuire, if you could keep sharing, and then I'll just
sure.
ask you to
Just say
switch
advance.
slides.
To
Okay,
do the old
great.
time kind of slideshow. Click, click.
Excellent. Okay, so sorry about that. Um, so we're going to move on to nitrogen and phosphorus environmental effects. Both nitrogen and phosphorus can contribute to water quality problems. This includes groundwater, where the nitrate limit is 10 parts per million, and surface water, where we can see eutrophication. For nitrogen, this is a primary concern in estuaries or the Chesapeake Bay. And then for phosphorus, this is a primary concern in freshwater. Next slide, please. And so the different nitrogen forms for inorganic, or what plants can take up, we have ammonium and nitrate. And then plants cannot take up nitrite, gaseous nitrogen, ammonia, and nitrite, I believe. And then some crops can also take up organic sources like amino acids and sugars, proteins, and other complex compounds, as well as decomposition can produce plant available nitrogen. Next slide, please. And so we're going to be focusing on the nitrogen transformations. This is the nitrogen cycle. We're going to be focusing on the transformations that are circled here in this diagram. Next slide, please. And so for our first transformation, we have mineralization. This is the conversion of organic nitrogen to inorganic nitrogen. As you can see, we have NH2 being ammonified into ammonia and water, which then turns into ammonium and hydroxyl. This is dependent on the carbon to nitrogen ratio. So nitrogen will only mineralize when the carbon to nitrogen ratio is below 20:1. And for soil organic matter, 97 to 99% of that is total soil nitrogen. Next slide, please. Our next transformation is nitrification. This is the conversion of ammonium to nitrite and then nitrate by soil bacteria. And so those are the nitrosomonas and nitrobacter. And so for that first one, we have ammonium and oxygen with the nitrosomonas will turn into nitrite and water, as well as some hydrogen ions. And then we'll take that nitrite plus some oxygen, and then the nitrobacter will transform that into nitrate. Nitrate is the most commonly uptaken form of nitrogen, but it can be subject to denitrification, leaching, or erosion or runoff. Next slide, please. And so some of the factors affecting mineralization and nitrification include pH, moisture, temperature, and aeration. Next slide, please. And so soil acidification via nitrification. Nitrification of ammonium generates hydrogen ions like you saw with those chemical reactions in the last few slides, which will reduce the soil pH. And the use of ammonium-based fertilizers will also decrease the soil pH through nitrification. And so this is the reason why, or one of the significant causes of liming needs. Next slide, please. And so another one of those transformations is immobilization. This is the conversion of inorganic nitrogen to organic nitrogen, so the opposite. This is when ammonium or nitrate transforms back into those organic nitrogen compounds. This is also dependent on the carbon to nitrogen ratio. Nitrogen will come immobilized whenever the carbon to nitrogen ratio is above 30:1. Next slide, please. And so another one of those transformations is ammonium adsorption. This is the retention of positively charged ammonium ions on the surface of soil colloids. And so ammonium is positively charged, as you can see there. And the mineral surfaces of soil clays are negatively charged. So those ammonium ions are attracted to that negative charge and will adsorb onto the clay surface. They can also become fixated. So this is the entrapment of ammonium ions between the platelets of certain clay minerals. Next slide, please. We can also experience losses of nitrogen. This includes volatilization, which is gaseous loss, leaching, which is downward soil transport, runoff, which is transport across the landscape, and then through crop removal, as the plants take up the nitrogen. Once the crop is removed, there's a nitrogen loss. Next slide, please. And so we'll go a little bit more in depth with that. So we see ammonia volatilization, which is ammonium and hydroxyl going back into ammonia and water. That NH3 is ammonia gas. And we see ammonia losses when there's a high pH and surface application of manure or ammoniacal or urea fertilizer. As you can see in this urea hydrolysis reaction, we have nitrite, hydrogen, and water. And urease is like a microbe that'll break that down into ammonium and hydrocarbonate. And then it'll take that ammonium and that will turn into the ammonia gas. Next slide, please. Then we have denitrification. This is the reduction of nitrate to gaseous forms of nitrogen by soil bacteria. And so whenever nitrate is being reduced, this is kind of like losing your oxygens almost. So we go nitrate to nitrite, nitrite to nitric oxide, nitrous oxide to dinitrogen gas. This occurs under anaerobic conditions or where there's no oxygen. And so bacteria will use nitrate as their electron acceptor for energy transformations. This type of transformation is favored at high pH or alkaline soil conditions. Next slide, please.
Just to expand on that a little bit, this is what a farmer doesn't want. So everything in the previous slides is how you get nitrogen to be plant available. This is losing plant available nitrogen, so it's something that farmers do not want to see. And microbes use oxygen when they break down organic matter. They would rather take it from the atmosphere, but it's in situations where they can't get it from the atmosphere that you get problems. So you see this a lot in waterlogged areas, and you also see it in like where rainfall puddles up in flat areas, or in the mountains where you have wet weather springs and you might have an area that's a little waterlogged for a while. The corn will go green, from green to yellow in those waterlogged areas. Sorry to interrupt, Paige. I'll put on the next one.
Please interrupt whenever you feel it is necessary. So this is a demonstration of leaching or our losses of nitrate. This is the difference between nitrate movement in sandy versus clay soil. It's much more likely to lose nitrate in sandy soil because sandy soil has worse water holding capacity. It's got these larger grains, so there's more space in between the grains, causing the nitrate to flow with the water all the way down into the groundwater, whereas clay has much better water holding capacities. It's able to slow down that movement of nitrate. Next slide, please. And so some of the factors affecting leaching of nitrogen include heavy fertilizer nitrogen applications on sandy soils, like we mentioned before, over application of manure and biosolids, improper timing of application, which I'll go a little bit more in depth the next slide, and then periods of exceptionally heavy rain all negatively impact nitrogen leaching. Next slide, please. And so this graph is showing how the percentage of total nitrogen taken up by plant is affected by the days after planting. So you can see that nitrogen is at its peak kind of during that tasseling stage. And so the best times to apply nitrogen would be at the start of the season to ensure availability, and then at that middle tasseling phase, you would apply sidedress. That would be your main application, because that's whenever the crop would need nitrogen the most. Next slide, please. And so moving on with our transformations, we have biological nitrogen fixation. This is the conversion of atmospheric nitrogen to an organic form of nitrogen. Symbiotic organisms and free-living organisms are capable of this. An example of that would be legumes. They have these root nodules that are able to do this transformation. So we have our atmospheric nitrogen here, and with a hydrogen ion and electrons, that will turn into ammonia and hydrogen. Next slide, please. And so this is showing the residual nitrogen credits for legumes, just kind of going deeper into the effects of legumes on nitrogen. This chart's basically showing that as the percentage of stand increases, your fertilizer needs for the following crop will decrease. So for example, we have a 50 to 75% stand of alfalfa, and the residual nitrogen remaining would be 90 pounds per acre. But as that stand decreases at 25 to 49%, the residual nitrogen is only 70 pounds per acre. So the higher percent stand that you plant, the less that you will eventually have to apply to the following crop. Next slide, please. Now we're going to be moving on to phosphorus.
Just any questions on nitrogen before we move on to phosphorus?
Yes.
Stephanie?
None in the chat, but I'm going to say understanding the nitrogen cycle, especially if you're taking the exam, is really, really important. It drives basically all of nutrient management, and knowing what volatilizes versus what leaches more, it's incredibly helpful. So this presentation and then piggybacking with the Mid-Atlantic Nutrient Management Handbook, very important. Still nothing in the chat. We'll let you know if something pops up though.
Okay, great. Thanks so much. So yeah, we're going to move on to phosphorus now. This is the phosphorus cycle, and the transformations that we're going to be focusing on are between soil solution phosphorus, mineral phosphorus, and sorbed phosphorus, specifically precipitation and dissolution between soil solution phosphorus and mineral phosphorus, and then adsorption and desorption between soil solution phosphorus and sorbed phosphorus. Next slide, please.
And just to emphasize we talked about this in one of the questions about why is nitrogen so much more complicated. In the red circle is all the chemistry we do in the soil testing lab for phosphorus. Everything we're trying to understand for nitrogen is on the left in that organic circle. So organic phosphorus, we know it's there. It may be about a third or a quarter of the phosphorus. We just ignore it in soil testing. But for nitrogen, everything is about the organic matter.
Great. So some quick facts about soil phosphorus. Total soil phosphorus is typically between 800 and 1600 pounds per acre, and 50 to 70% of that is in inorganic forms. This, however, has low solubility, meaning it's mostly unavailable for plants. Roots absorb phosphorus from the soil solution, typically less than 0.01 to 1 parts per million, but 0.2 parts per million is adequate for plants. And so the soil solution phosphorus must be replaced continuously. Next slide, please. So how can phosphorus be plant available and not leach? We're going to get into that. Next slide. And so this graph is showing the whole year for soil nitrate. You see it peaks in June, and then there's another smaller peak around October, November. Whereas soil solution phosphorus is stable throughout the whole year. Next slide, please.
And just to expand a little bit on that, this is the reason why we don't soil test for nitrogen for the most part, other than the pre-sidedress nitrate test that you're going to be learning about later. But if you look at this December, January, February, the soil is cold and wet, so the microbes aren't actually breaking down organic matter and making plant available nitrate. It's also the time of year where you have not a lot of evaporation, and you get most of your leaching. And then March, April, May, as things warm up, the microbes are getting going, they're breaking down the organic matter, they're releasing nitrogen. And then after that peak, this is under corn, so suddenly the corn starts taking up that nitrate very rapidly, so the soil nitrate drops off. And then as the corn matures in August, it stops taking up nitrogen, and the soil's still warm, so the nitrate goes back up again. But this is why we don't soil test for nitrate. For the most part, we can, but it's very weather dependent, and it changes depending on the year.
All right. And so our forms of soil solution phosphorus are hydrogen phosphate and dihydrogen phosphate. What they both have in common is that orthophosphate, which is the PO4 that you see. This is a building block in a lot of different biological processes. Next slide, please. And so for phosphorus transformations, organic phosphorus, which is your animal manures, biosolids, plant residues, humus, and what your microbes break up, is 30 to 50% of your soil phosphorus that mineralizes into your inorganic phosphorus, which is fairly insoluble, like we mentioned. But this inorganic phosphorus, the reason why it's insoluble is because it adsorbs onto mineral surfaces like your clays, iron and aluminum oxides, and carbonates, and then precipitates into secondary compounds like this aluminum phosphide that you see here, which effectively locks the phosphorus away, making it insoluble. And so over the next few slides, we're going to kind of break that down a bit. So for phosphorus adsorption, if you're thinking about nitrate, it doesn't readily, because it's so highly mobile, it doesn't readily adsorb onto this aluminum oxide surface. It also doesn't have any hydroxyls to exchange. But if you're thinking about, let's say, a hydrogen phosphate, this will exchange your hydroxyl and then become what's called labile phosphorus, which means it's loosely bound and readily converts to your soil solution phosphorus, which helps maintain equilibrium in the soil. Over time, however, this hydrogen phosphate exchanges both hydroxyl and water, which makes it fixed or non-labile, making it unavailable to plants and causing that low solubility. And so some of the factors affecting phosphorus availability include the amount and type of clay. High clay soils retain more phosphorus, and kaolitic and oxide clays retain more phosphorus. The time of application is another factor.
Uh-oh, I can't.
Soil phosphorus.
Oh, we lost you for a second. Sorry, Paige.
Oh, no, it's
We
okay.
lost you halfway
You can
through
hear
the
me okay
second
now?
bullet. Yep, we lost you halfway through the second bullet.
Okay, gotcha. So for the time of application is also a factor. The longer the time of contact there is, this increases the chances of fixation. Kind of like how I mentioned in the last slide, over time, the phosphorus will become fixed. And then lastly, the phosphate status of the soil is also a factor. The more soil phosphorus there is, the more available it will become. Next slide, please. Other factors, acidic or low pH soils, the availability is low because phosphorus is tied up as iron and aluminum phosphates. And then similarly, in alkaline, basic, or high pH soils, availability is low because phosphorus is tied up in calcium phosphates. So the optimum range here is between 5.5 to 6.5 pH. Next slide, please. And that's kind of showing this optimum range here. You can see the three different peaks, specifically two on your left-hand side is your acidic soils, and then on the right is your alkaline soils. And then you've kind of got that sweet spot in between 5.5 and 6.5, where phosphorus is most readily available. Next slide, please. Okay, so we're going to be talking about phosphorus and water quality now. Next slide. So we're comparing here the movement of nitrogen versus the movement of phosphorus. We've mentioned this a few times now, but nitrate is far more likely to leach compared to phosphorus because it's much more dynamic, whereas phosphorus is stable and is more likely to adsorb and fix onto the soil particles. Next slide, please.
And this is important in situations like no-till, when you surface apply a phosphorus fertilizer and you don't till it in. You generally find that most of the phosphorus is held in the top inch or two, which is why our soil sampling methods recommend a shallower sampling where you have no-till and where you have tillage, whereas nitrogen moves freely down the soil.
Okay, so we're going to be talking about the pathways of transport for phosphorus. So on the surface, we have runoff, erosion, specifically stream bank and bed erosion or deposition. And that's is going to be your particulate phosphorus and soluble phosphorus. We also have subsurface transport, which is leaching to groundwater via cracks or tiles. And then we have biological pathways of transport, which is the uptake and release, through different animals or plants and whatnot. And then the factors influencing transport include manure, fertilizer application, as well as like heavy rain events will dramatically impact the surface and subsurface transportation. Next slide, please. So how important is soil erosion? So like we've mentioned before, phosphorus strongly fixes to soil particles. So when soil erodes, this carries a significant amount of phosphorus away from the fields. If you go to your next slide, you can see that there are some erosion control barriers trying to be put in place here. These are silt fences that are in an attempt to prevent surface phosphorus loss. But because of how strongly phosphorus fixes to soil particles through soil erosion, we're seeing a depletion in soil fertility. And if you go to the next slide, we'll also be seeing nutrient pollution or eutrophication in water bodies. So it's important to test for soil phosphorus in order to avoid these, in order to guide fertilizer application. Next slide, please.
Just one of the things about this slide is in a storm you can see the brown water coming off the edge of a field and erosion, but it's hard to see what impact that has at scale. So in this photograph at the top, you've got the Susquehanna River and the Delaware River, and there's obviously been some very, very heavy rainfall up there, and the soil has been eroded. So you see the scale of how much that soil impacts something like the Chesapeake Bay in terms of how much soil is actually ends up going from farmers' fields into water bodies.
So for this next slide, this was a study looking at phosphorus applied as poultry litter versus crop removal. So the main idea here is that the corn has a higher nitrogen to phosphorus ratio versus the poultry litter, meaning it's not going to be taking up all of that phosphorus that's being applied as poultry litter, causing an imbalance between your nitrogen and phosphorus in your soil, and ultimately leading to nutrient pollution. So it's important to test your soil here to make sure you're not experiencing that imbalance. Next slide, please. And so this graph is showing your relative yield percentage with increasing extractable nutrient. So for your relative yield, that will increase up to a certain critical value, and then it sort of stabilizes. Whereas put up against phosphorus loss and surface runoff, there is no critical value for phosphorus loss. So that's just going to continue to rise as your extractable nutrient increases, leading to environmental problems above that critical value. Next slide, please. This was a study done in the Shenandoah Valley looking at dissolved reactive phosphorus against soil test phosphorus. As you can see, as soil test phosphorus increases, so does dissolved reactive phosphorus. And most of those measurements are above the 0.1 milligrams per liter phosphorus concentration, which means there is a potential for nutrient pollution or eutrophication. Next slide, please. And so I believe Dr. McGuire talked to you about this in the questions before, but this is kind of a demonstration of cash grain versus your dairy or your dairy farm. And so this is a cash grain. It's your more simple or straight through flow system. You'll have fertilizer going in and then harvested crops going out. And so here you can apply whatever chemical fertilizer you need without having to worry about imbalances. But if you go to the next slide, this is a diagram of a livestock farm. You can see this is more complex closed loop system where the nutrients go in, your fertilizer and your feed, and your nutrients come out with your crops and your animal products. However, there will be some nutrient losses to air and water as well as accumulations in the soil. So because of this, there are significant nutrient imbalances from your feed and manure due to excess phosphorus or excess nitrogen, because you can't exactly know unless you test, I guess, you know, how much nitrogen, how much phosphorus you're applying with the manure that you're producing on your livestock farm. Next slide, please. So this is showing manure phosphorus surplus across the nation. This is data collected by the USDA. And here we're looking at the difference between the Midwest and our Chesapeake Bay Mid-Atlantic region. As you can see, that surplus phosphorus a lot less in the Midwest region than in the Mid-Atlantic region. That is due to Midwest being a major corn and soybean producer, whereas here in the Mid-Atlantic, we see a lot of concentrated animal feeding operations. This is where, as we've talked about a bit in our livestock farm diagram, manure is meeting nitrogen needs. That's unfortunately leading to an over-application of phosphorus. And that has a lot to do with, like I mentioned, Midwest is a major crop producer that has a lot more land to spread that application out, whereas here we have limited cropland potential. And so it's only about 10% of surplus phosphorus throughout the nation. But if we were to spread that out or spread our cropland out, we might be able to see even less. And so here we're looking at the agronomic soil test phosphorus in Virginia for commercial samples. You can see it's pretty high, like the Shenandoah Valley region. Just as a poll, our next slide is going to be looking at this same measurement for homeowners. What do we all think that might look like?
Anyone? Do you think homeowners or farmers do a better job?
Who's putting more money into this? Farmers do better from the chat.
And you would be
That's
right
good.
if you want to click over to that next slide. Yeah, the entire state for lawn and garden samples are above 10% for their soil test phosphorus. And that's most likely because home gardeners are more likely to adopt that more is better approach when it comes to fertilizers, and then less likely to test for soil phosphorus, which leads to a surplus in phosphorus. Next slide, please. And so what we're looking at here is another study where we had 20,000 broilers worth of poultry litter applied to 150 bundles per acre of a corn crop. And so if you look at the bottom here, we've got 20,000 birds, 6 flocks. We're adding 1.25 tons per 1,000 birds, which is equating to 150 tons. And so we're applying at a rate of 4.2 tons per acre, which is giving us that 150 pounds of plant available nitrogen. But whenever we're meeting the needs of nitrogen, we're going to have a surplus of phosphorus. But if we are looking at meeting the needs of phosphorus, on the other hand, applying poultry litter, we're going to have a nitrogen deficit. So this is just another reason why it's important to test your soils to make sure that there's not this imbalance whenever you are fertilizing your crops. And then here we're looking at your typical crop nutrient removal. Essentially, this is showing that besides corn grain, phosphorus is usually removed the least. And then except for corn silage and alfalfa, nitrogen is usually removed the most. Just another example of that imbalance.
And this is important in nutrient management because one of the regulations is that you can apply manure at a phosphorus removal rate. So if you're having 150 bushels of corn, you can go in, find this number, multiply it by 150, and then work out how much manure you're allowed to apply.
So what are differences in nitrogen and phosphorus supply? We have our sources, release characteristics, and changes in soil concentrations. And then this final slide is from a study going on over 25 years. Essentially, they didn't apply phosphorus over that time, but they kept on planting corn. And it took just about 15 years of not applying phosphorus to get below that critical level. Yeah, I think that concludes my presentation. Dr. McGuire, do you have anything else to add?
Anybody have any questions before we go on to the next presentation?
Nothing in the chat so far, but NNP or N and P are definitely the heavy hitters and what we set a lot of our all of our regulations off of not over applying in, and in organic situations, managing the phosphorus as much as you can. So big, important nutrients for nutrient management. Still nothing, so I'd say we can crack on.
Okay, can you see my title slide?
Yes.
Okay, hello everybody, back to me again. I'm going to be talking about phosphorus mass balance on Virginia dairy farms. Okay, we're talking about phosphorus mass balance, but why aren't we talking about nitrogen and potassium? The reason for that is that if a farm imports more phosphorus than it exports, that phosphorus is going to be ending up in the soil and building up your soil test phosphorus. With nitrogen, as you well know, nitrogen nitrate leaches. So with nitrogen, every year you're pretty much starting back at scratch again. And for potassium, you can build up your soil test potassium, but it generally doesn't build up that much, and it doesn't cause any water quality problems. And if you take care of your phosphorus mass balance, you won't have to worry about nitrogen and potassium at all, because phosphorus can be the problem one if it's not managed correctly. So in nutrient management talks, you keep hearing about phosphorus being bad, but that's bad when it's too much. Phosphorus is wonderful. It's essential for life. All living things have phosphorus in them. We couldn't exist without phosphorus. It's the building blocks of DNA, cell membranes, energy metabolism. It's in all parts of our body. In us animals, most of the phosphorus is in our bones. It's calcium phosphate that gives our bones the substance. There's no substitute for phosphorus. If we don't have phosphorus, we can't eat something else. So, but why think about phosphorus efficiency? That's what we're really doing with nutrient management. The inefficient use of phosphorus within agriculture can lead to a buildup of phosphorus in the soils. So if you have too many animals and you're applying all of that manure to local soils above nutrient management recommendations, year after year, you're going to build up the soil test phosphorus. And we see this in areas with intensive animal production. Um, in areas with intensive animal production, diet and manure management can greatly affect the buildup of phosphorus. Due to environmental concerns, we have regulations now. When people started seeing agricultural nutrients ending up in water, regulations started prohibiting phosphorus applications above critical levels. We have an environmental threshold and of 35% and above 65% saturated, you can't apply any more manure, and that's based on your soil test phosphorus level. In terms of some of the imbalances that Paige showed you, why do we have these imbalances in manure? Why isn't the manure production spread out? It's because of the economies of scale. The soils in the Midwest are great for growing corn and soybeans, so a lot of corn and soybeans are obviously growing there. And then in our area, we're close to markets for meat, so it's very economically sustainable to have a feed mill, a slaughterhouse, and a lot of chicken houses or dairy or swine close to those facilities. So the economics of scale really drive when their manure is produced, not agronomics. And so the system we have was developed by economics, not on the need for those manure nutrients. But there are still things we can do and things that you can tell farmers to try and help them meet nutrient management recommendations, regulations, without getting into economic issues. So some more phosphorus facts. About 80% of the phosphorus that's mined never ends up in the food that's consumed. So obviously there's an opportunity to improve the efficiency if we're only using about 20% of what we fertilize with. The planet has 6 billion people, but 70 billion livestock. And that's why people ask me about what about biosolids, which comes from sewage treatment works. There's just not the volume of that there is of animal manure because we have so many animals. Some more phosphorus facts. We have historically mined a lot of phosphorus in America. Now, looking into the future, Morocco is probably going to be a major source for us. It holds about 40% of the world reserves. It's also very dry, so they don't have any water quality problems because they don't have any water. They can mine it in fairly arid areas. So our phosphorus production has already peaked and it's in decline. Canada doesn't have any reserves. They get theirs from ours or increasingly from Morocco and other places. So what's this concept of mass balance I'm going to be talking about? Elements are neither created or destroyed, so phosphorus isn't going to convert into anything else. Elements which enter the farm either exit the farm or are stored. With nitrogen, it can go into the atmosphere. There's no gaseous form of phosphorus. The composition of animal products, meat, eggs, is not significantly affected by the phosphorus in the diet, as long as you have enough in there. So if you overfeed phosphorus, there's going to be more and more phosphorus coming out the back end of that animal, and the animal's not going to benefit from it. And I'm going to talk a little bit about how quickly soil test phosphorus changes. So how many pounds of phosphorus does it take to increase soil test phosphorus by 1 part per million? Again, phosphorus versus nitrogen. We talked about this a little bit in the first talk. Why are we talking about phosphorus mass balance and not nitrogen? Phosphorus, if it goes into a farm, it ends up in the soil. There's no gaseous form. If you apply it to the soil, it stays there, and there's very little leaching. Whereas history of over-application of phosphorus shows up in elevated soil test levels. Nitrogen, if you over-apply, you're going to have a lot of leaching, and you largely start fresh every year. There's a small amount of carryover, but for the most part, you're starting fresh every year. It does not build up on soils. So in the regulations, you have once you get up to 65% saturated, you're not allowed to apply any phosphorus, which means you're not allowed to apply any manure. So depending on the region that you're in, so for example, Eastern Shore, Lower Coastal Plain, if you're above 458 parts per million phosphorus, you're not allowed to apply any manure. So these are obviously very high elevated levels. You only need 55 for maximum optimum crop growth. So these are well above those levels, but these are just to protect the environment, prevent excessive phosphorus losses. So land requirement, Paige touched a little bit about this, land requirement for nitrogen versus phosphorus management. She went through the example of the broiler house with 25,000 birds and 6 flocks per year. For nitrogen-based, you only needed 43 acres. For phosphorus-based, you needed 171 acres. Within the nutrient management plans, you can write a 3-year plan, so you can do a nitrogen-based application 1 year, and then just come back with nitrogen-only urea or something like that the next 2 years. So you basically apply enough phosphorus for 3 years in 1 year application, and then don't apply any for the next 2 years. So dairy farmers, they have an issue. If you have a cow plus replacement, you can end up with about 70 pounds per acre. So what advice would you give poultry dairy farmers about long-term sustainability and BMPs? What can you tell them to try and So one of the first things I did when I started here, almost 20 years ago, I finished up a 7-year study initiated by my predecessor. I'm going to be talking mostly about the ones in blue here. He did a study where he applied no phosphorus. He applied a nitrogen-based litter application. So he's over applying phosphorus, applying the correct amount of nitrogen. He did number 4 there, the phosphorus-based litter application. So he's trying to apply removal rate. He did this with both the TSP, is the triple sulfur phosphate, the chemical fertilizer, but over time it didn't matter if they used poultry litter or chemical fertilizer. They were just farming corn and either over applying or under applying phosphorus based on the soil tests. This was continued for 7 years. The soil test phosphorus was always sufficient, even where no phosphorus was added because it was above that 55 parts per million. Mostly corn silage, some hay. Yields were the same across all treatments. So I'm only going to talk about what happened to the soil test phosphorus, where they either over applied it or mined it out of the soil with the crop. So this is an example of one of the figures. So on the y-axis, we have your soil test phosphorus level, your malic one, and across the x-axis, we have year. And you can see that for the different treatments, there are different colored lines. But what I'm going to do is mainly focus on what happened after 7 years of these treatments, focusing in on the difference between over-application versus under-application of phosphorus. So here's a case in Rockingham County in the Shenandoah Valley. So the phosphorus mass balance, where you had no phosphorus, they mined out 364 pounds of phosphorus per acre. For where they're doing the nitrogen-based application of litter, they're over applying about 618. The change in soil test phosphorus was about 55 parts per million. So the difference of the difference between minus 364 and positive 618 is 983, and the difference in the soil test phosphorus at the end was 55 parts per million. This is another one for another site in Page County in the Shenandoah Valley. So again, no phosphorus where they're growing corn with no addition of fertilizer. They managed to mine out 447 pounds of phosphate over 7 years. Nitrogen-based litter application, they were over applying about 376 pounds. So that's a difference of 823. And that led to a difference in the soil test P at the end of the 7-year study of about 59 parts per million. And another third site, but it's again the same thing, either mining or over applying. The difference between mining it and over applying was over half a ton, about 1,202 pounds, and that made a difference of about 53 parts per million after 7 years. So soil test P doesn't change very quickly. So summary for all 3 sites. We have the phosphorus mass balance, the difference between mining it and over applying, the change in soil test phosphorus. So you divide the phosphorus mass balance by the change in Mehlich 1 phosphorus, and you end up with how many pounds of phosphorus does it take to change your Mehlich 1 by 1 part per million. And on average, it's about 18 pounds. So one of the questions I asked in the first presentation is how quickly does soil test phosphorus change? And a corn crop, if it takes out about 50 pounds, you're only going to be changing your soil test by about 2 or 3 parts per million a year. So if you add more than you remove, if you add more than you remove, you increase soil test P and vice versa. It takes in the ballpark of 18 pounds of phosphate to increase or decrease your Mehlich 1 by 1 part per million. Depends on soil type, but it's obviously going to change very slowly over the years. If you have something like a 400 parts per million soil, it's going to take you decades to decrease the soil test phosphorus in that soil back down to where you would need to apply it again. So we have something fairly new, the Virginia Dairy Phosphorus Mass Balance Project. Poultry versus dairy mass balance strategies are very different. Poultry is very easy. Something like 80 to 90% of poultry litter is exported from farms. It's a dry product. It's maybe only 30% moisture. So there's a big demand for poultry litter from farmers, and there's a strong industry of collecting it, transporting it, and spreading it. Dairy manure is a lot more complicated. It's about 95% water, so it doesn't get transported very much because you're paying to transport water. All poultry feed is pretty much the same, whereas every dairy is different. They're different in imported feed, animal density, and some can grow more, have the ability to grow more of their own feed. So every dairy is a little bit different. Poultry is fairly straightforward, which is why we're concentrating on dairy. So I'm going to take a minute to explain this chart. This is some work out of New York that we replicated here in Virginia. It's trying to show that the phosphorus mass balance is unrelated to milk productivity. So on the y-axis, there's phosphorus balance. On the x-axis, there's milk production in thousands of pounds. The diagonal black line has 50% of the sites above it and 50% of the sites below it. It's showing that, and the horizontal line, 75% of farms are less than 12 pounds per acre. And this is considered to be the product where soils or dairy farms are most productive. So in this green area, you both have high milk production and relatively low mass, excessive mass balance. And then you can see the colored dots. the red dot is from 2005, where they worked with this one farm, and they had 16 to 17,000 pounds of milk per acre. And as they worked with them with several strategies, they were able to decrease their phosphorus mass balance without decreasing their milk production. Farmers need to maintain milk production for profitability, but it's trying to work with them on several strategies we're going to go through to try and work out how can they be sustainable in terms of mass balance, but also maintain milk production. So we did this on 44 dairy farms across Virginia in 2017. So again, the diagonal line is the efficiency. 50% of the farms are above it, 50% are below. The ones below are being more productive per milk production. And then the horizontal line is a feasibility. If it's feasible for 75% of farms, it should be feasible for all of them. So what are the strategies that the different farmers were used to try and increase their product or maintain productivity, but not have this excessive import of phosphorus that's going to get you in trouble with the your phosphorus soil test phosphorus level. So comparing these two farms, Farm A and Farm B, they have similar milk production, but obviously their phosphorus mass balance is very, very different. So when we compare them, Farm A has a positive balance of about 100 kilograms per hectare, whereas Farm B is actually exporting more phosphorus than importing. The land base is the same, so the number of acres is the same. Milk production is about the same, and the number of cows is the same. So what is it that gives one of these farms very high phosphorus mass balance and the other one a low phosphorus mass balance? One of them imports a lot more phosphorus in terms of feed. The other one is very good at growing its own feed. So some farmers can get more corn yield, and some rely more on imports. Both of them have poultry, so they have, as well as dairy, they also have poultry, which is fairly common in Virginia. And one of them exports all of that poultry litter, whereas the other one keeps it. And so that's really the big difference in terms of why one uses the dairy manure plus the poultry litter. One uses their dairy manure and exports their poultry litter. So it's a very simple management change for farmer, where they can meet the nutrient management recommendations and not build up their soil test phosphorus, where they're going to get in problems with regulations in the future. We looked at different things. Poultry litter applied. About 3/4 of the farms that use poultry litter were above this is out of balance, and this wasn't a great surprise because the dairy farms already have manure and they can use that dairy manure productively. But when you have poultry litter on top of that, and that poultry feed is 100% imported, then you can get into problems with mass balance. Feed imported per animal unit. There was a slight link, but not a great link. But you can certainly see some of the farms were below zero exporting. They generally had less feed imported, and a lot of the higher ones had more feed imported. We looked at certified organic. They tended to be lower production. They were in the feasibility range, but not in the efficiency range because of their productivity being low. We looked at animal density, and one of the things we saw was that larger farms with more animal units and with more cows, they tended to be more efficient. So in the New York study, they found where there was higher animal density, more animals per acre, they had more problem with phosphorus balance. But down here in Virginia, we found that the farms with higher animal density also had more animals, and they were more dialed in on what they were feeding those cows. So it wasn't an issue down here in Virginia. Some mass balance strategies. Pay attention to mass balance for the sake of the farmer's future. You don't want to be building up soil test phosphorus in a farm over time. If you keep building it up year after year, you're eventually going to reach a situation where your soil test phosphorus gets high enough, you're not going to be allowed to use manure anymore. If you come across a dairy farm that has a phosphorus mass balance problem. Here are the strategies you can use. You don't want to be decreasing their animal numbers, so these are some productive strategies that those farmers can use. Don't buy poultry litter as a nitrogen source. Don't buy it, or if you have poultry of your own, export it. Export that manure. Try to grow rather than import your feed. Work with an agronomist to increase your corn yields. Some farmers have managed to export value-added products. They can compost their manure and sell it, so it's a way to sell a value-added product. Avoid dry distillers grain. We get some from ethanol plants in Virginia, and we also have the Coors plant. But dry distillers grains, basically where you take corn, you take out the energy, and all of the phosphorus is left. So dry distillers grains are mostly corn with the energy taken out. So the phosphorus is concentrated up. Some farmers can rent more land or spread some manure on their neighbor's farm. And there's some research to show you don't need starter phosphorus if your soil test phosphorus is above 55 parts per million. Other options for economics, and you certainly don't want to do that to farmers you're dealing with. Any questions? And that's the end of that talk. And close to being on time. I think it was meant to end 5 minutes from now.
Hey, we won't ever quibble about being a little ahead of schedule. No questions so far. If you think of anything, drop it in the chat, ask it when we get back. But if no questions, be back at 2:45 for some more organic nutrient source information. Very interesting stuff. Very important to the exam and nutrient management in general. So see you guys in 20-ish minutes.
And if you think of any questions while you're away, I can answer them at the start of the next session.
Yes.